You know that feeling on a Friday night where you want to be at a concert, front row,
Right.
but you also really want to be in bed with a book.
Happens every time.
And it's physically impossible, right? You've got to be either here or there.
Unless it seems you're a tiny chunk of sodium metal.
Exactly. That's what we're digging into. There's this new study just out on Nature last month.
The title is a bit of a beast. Something like Probing Quantum Mechanics with Nanoparticle. You know?
Yeah, it's a mouthful. But the mission is really simple.
Yeah.
It's all about blurring that line between the weird quantum world and, well, our world.
And they have blurred it. A lot. They took these massive metal clusters and essentially forced them into a superposition state.
So they were literally in two places at once.
They were.
And when we say massive, we really have to stress this. This isn't just one lonely electron.
No, not at all. These were sodium nanoparticles. We're talking about between 5 and 10,000 atoms all clumped together.
Wow.
It's a huge scale up. In terms of sheer weight, the clusters are over 170,000 daltons.
Which puts them in the same weight class as actual biological stuff, right?
It does, yeah. They're heavier than something like the coconut cadangviroid and even an IgG antibody.
Yeah.
We're really approaching the mass of small viruses.
So how do you even do that? How do you take something that heavy and make it act like a ghost?
They use this incredible setup they call MSLE. Stands for multi-scale cluster interference. It's basically built around a device called a Talbot-Lau interferometer. Just think of it like a series of really, really fine fences made of light.
Okay, so they shoot these sodium clusters through the light fences, and instead of just picking one path...
The cluster's center of mass it delocalizes. It goes through multiple paths at once. It enters a Schrödinger's cat state.
So it's here and there at the same time.
Exactly. And the distance between those two states wasn't trivial. It was 133 nanometers.
That sounds tiny, but for the particle itself, that's more than 10 times its own size.
It is.
It's like me standing here at this mic and also somehow standing over there by the coffee machine.
That's the perfect analogy. And this result really, it really challenges the macrorealist view of the world.
The idea that quantum mechanics just sort of switches off once things get big enough.
Precisely. That the universe forces things to pick a spot. But this experiment shows the standard Schrödinger equation holds up beautifully.
And they measure this, right, with a macroscopicity score.
They did. They got a value of 15.5.
Which is good.
It's incredible. It completely smashes the previous record by an order of magnitude.
Speaking of, optimizing complex systems to get incredible results, that actually reminds me of our sponsor, Embersilk.
Right. If you're trying to streamline your own work with AI, whether it's automation or complex software development, Embersilk are really the experts.
They're amazing at uncovering where AI agents can make the most impact for your business or even just your personal life. You should check them out at embersilk.com.
So back to the paper. Where do we even go from 170,000 daltons?
Well, the authors are already talking about the next big goal, the million-dalton range.
A million? I mean, that's just wild. At that scale, you could perform these same quantum interference experiments with actual viruses.
Like the satellite tobacco necrosis virus. Just
Yeah.
picture that for a second. A virus is a complex biological machine, and we're talking about putting the whole thing into a wave state.
It's a truly bottom-up way of understanding the universe. If we can keep scaling this, we might finally get to a point where we can test the interface between quantum mechanics and gravity.
It really makes you look at the chair you're sitting on a little differently, doesn't it?
It does.
Technically, all that solid matter is capable of behaving like a wave. It's not a law of physics stopping it.
It's just a problem of isolation. It makes you wonder if classical reality is just an illusion of scale.
And that's the question to leave you with, isn't it? If a chunk of metal with 10,000 atoms can be a wave, at what point does our solid classical world actually begin? Or is it all just too messy for us to see the magic?
It's a wonderful thought to chew on.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out.
Thanks for tuning in.